Alright, here we're going to look at 8.7, factoring special cases. Now before we do that, I want us to remember that factoring is just the opposite of FOIL. Now, back in a previous lesson, that lesson being 8.4, multiplying special cases, we looked at scenarios such as this. We saw x plus 4 squared, and I encouraged everyone to think about what that really meant. X plus 4 squared was really x plus 4 times another x plus 4. So this one would have been x minus 2 squared. And then this one would have been 3x plus 5 squared. And there is a formula that was used, and we found out that we got the middle term twice, the same middle term twice that we'd combine when we did FOIL. So let's see what I'm talking about here. When we do x times x, we get x squared. And then, because of the symmetry, we're going to get the same term twice. I'd get an x times 4 and another x times 4. So we'll get a plus 4x and then a second plus 4x. And then we have the 4 times 4 to get the plus 16. And when we combine those together, 2 in red, we get x squared plus 8x plus 16. Alright, and that formula involved us talking about how anytime we're multiplying a case that started off something squared, we're going to get matching middle terms. They're going to show up twice because of the symmetry. So on this one, when we multiply it out, we get x squared minus 2x plus a 4 to get x squared minus 4x plus 4. And then on this one, we'd get a 9x squared plus a 15x plus a 15x plus a 25. And that would simplify to 9x squared plus 30x plus 25. Now, what it's asking here says, what do you notice about the first and last terms in all of your answers? What we're going to be looking at today for when we're factoring this, now all the first terms here are invisible ones. So 1, 1, and then this one's a 9. What this is asking you to recognize is that all of these numbers are perfect squares. They are all perfect squares, right? And I'll just list them out. We had the number 1, right there. We had 16. We had another 1 right there. We had a 4. We had a 9. And we had a 25. Right? All of those numbers are perfect squares. And what that means is that we could square root any of those numbers and get a whole number answer. What that means is we call the above perfect square trinomials. Perfect square trinomials come from any time we multiply a term by itself. All right, the first and last numbers are perfect squares, meaning we can take their square root. How this will help us is that anytime we're looking to factor and we notice that I've got a perfect square out front and I've got a perfect square here, we can check and see, is this going to be a perfect square case? Now, the good news is, even if you never watched this video, you would still be able to factor this. Because worst case scenario, you'd recognize, hey, this is the easy type of factoring because it's a 1 out front. So you'd start x and x, and then you'd be looking for numbers that multiply together to give me 36, that also add together to give me a negative 12. You would come up with negative 6 and negative 6. The only thing that's new for this lesson is anytime you get two factors that are identical, you need to write your final answer in the proper way, which will be condensing it back into x minus 6 squared. So, as mentioned at the start of this video, all we're doing is working backwards. On the first part of this chapter, you would have started with this. I would have said FOIL it, and you would have gotten that answer. Now, I'm giving you the answer, and you have to factor it back to its original template. So for this next one, you might recognize, hey, that's a perfect square. Maybe my answer is 5 and 5. All right, and then you'd also need to take a look at the signs and recognize they do both need to be positive, because I need it to multiply together to give me a positive 25, and also add together to give me a positive 10. So this one is x plus 5 squared. But once again, you don't even have to know and recognize when the numbers are a perfect square, because you could always factor it from the traditional standpoint. I do need you to recognize, though, if you have x plus 5, that needs to become x plus 5 squared. It is incorrect to leave it as x plus 5, so you would lose test points if you did not switch it to x plus 5 squared. And you use the squared forms a lot in Algebra 2. So we're practicing a skill that we need for much later right now, to where anytime you have the same term twice, you need to condense it down. This one, noticing that this is a 49, it's going to be x plus 7, x plus 7. So this would be x plus 7 squared. Now here's where this can really help you out. These are the more difficult type, right? And we can see that here because the number out front is not a 1. Now, you might recognize that both of these are perfect squares. You might also recognize or remember that the first step, anytime we're not working with the easy type, and the easy type's when it's a 1 out in front, the first thing to do is to check for a greatest common factor. This one does have a greatest common factor. Its greatest common factor is 4. So when I divide all those numbers by 4, I'll get an x squared plus a 6x plus a 9. Now that we have that GCF taken care of, what we're looking to do is factor the remaining portion. And you might recognize, hey, there's still perfect squares. I've got a 1 and a 9. So that's telling you to check, could the answer be x plus 3, x plus 3? And that does work, because 3 times 3 gives me 9, and 3 plus 3 gives me the 6. So this final answer would be 4 times x plus 3 squared. Sometimes when you look at these, though, there will not be a GCF. There's not a number that I can divide all of these by. But if I tell you that this is a perfect square, so let's assume I say this is a perfect square trinomial. What that means is we're going to look to factor it using square roots, to where, what's the number multiplied by itself that gives me a 9? It's 3 and 3. What's the number that multiplies together to give me a 49? 7 and 7. Now you might notice I'm making them negative, because I need them to multiply together to give me a positive, and add together to give me a negative. But you might be saying, hey, Mr. Connell, that can't be right, because negative 7 plus negative 7 doesn't give me a negative 42. I'll challenge you to remember, whenever we're working with the more difficult type, so there's a number out in front, the middle term does not come from adding the negative 7 and the negative 7. It instead comes from multiplying the O and the I of FOIL and adding them up. So 3x times a negative 7 is a negative 21x. Then we get another minus 21x. Those combine together to give us that negative 42x. So that means that this answer is indeed correct, but we would need to shrink it down to 3x minus 7 squared. Now, this is beneficial because if I didn't tell you this was a perfect square trinomial, what you would have had to do is you would have had to check different combinations of 3x and 3x, different combinations of 9x and x, also thinking about the factors of 49, right? The amount of combinations could have been much larger to check, but I didn't need to check any of those because when I tell you it's a perfect square trinomial, you're looking to square root the different numbers. And once again, even if you didn't watch this video, you could have still factored this guy by going through the processes we covered in 8.6, and you would have came to the conclusion that the factors are 3x minus 7 and 3x minus 7. Just remember to now shrink it down to 3x minus 7 squared. So, whenever we're working with these special perfect square trinomials, they'll either factor to double positive or double negative, which then would need to be shrunk down. And that's perfect square trinomials. This one here, one last one. Do recall, anytime you recognize that we're not working with the easy type, check for a GCF. This one does have a GCF. It would give us, after I pull out a 4, 4x squared plus 4x plus 1. Now, the 4 will stay, but I encourage you to pause the video and think if you can figure out what does this factor to. And it is a perfect square trinomial. Using that knowledge, see if you can pause this video and see what it factors to. And then when you push play, I'll reveal the answer. The answer to this is 2x and 2x, because that's the square root of 4x squared. And then when I square root the 1, it's plus 1 and plus 1. So this final answer would be 4 times 2x plus 1 squared. Now, a question you might have is, Mr. Cottle, could I not have factored this original one because they're both perfect squares? Couldn't I have called this 4x plus 2 and another 4x plus 2 and said my answer is 4x plus 2 squared, like that? That is the same mathematical value. However, in order to have answers fully correct, you do have to pull out GCFs. So for on this one, there's a GCF of 2. And on this one, there's a GCF of 2. And that 2 times 2 is what gives us our 4. So you do need to pull out GCFs in order to have the correct answer. If you FOILed it out, this FOILs back out to the exact same thing as this, but the math community has agreed that everyone must pull out greatest common factors in order for answers to be fully correct. There was another type of special case we worked on as well, where the signs were opposite. Right? Everything on the inside was the same, but one was positive and one was negative. And when you see those here, you might remember that when you FOIL, it caused the middle term to cancel out. X times x is x squared. Then we'd get a positive 4x and a minus 4x. And then minus 16. And the middle terms always canceled out. And that was true anytime we were FOILing and we had the exact same terms, but the signs were opposite. And essentially what that means is we don't even need to check the middle terms. All we're really doing on these are the outside terms, because these ones in red are going to cancel out anyways. So essentially, we could skip those two red ones and have 4x squared minus 9. Now, notice how these didn't start off in a squared form because the signs are opposite. And when the signs are opposite, there's no way to express it down to the same thing twice because they're different. What happened to our middle term? It went away due to the opposites. All right, these are called the difference of squares because the signs are different. One's positive and one's negative. And it's similar to the other side where the two terms are perfect squares, but the middle term cancels. These are by far the easiest type of factoring to do. You can always identify them because they will be two terms, right? All the previous ones were three terms, so these look very different. And you don't even have to think very hard because on every single set, one will be positive and one will be negative. Anytime you see the two-term setup, that's going to be the case. One positive, one negative. Then beyond that, you are square rooting your terms. So the square root of x squared is x and x. Square root of 25 is 5 and 5. If you FOIL this out, you'll get right back to the answer of x squared minus 25. This one would be x and x, 7 and 7. Now, the only thing that confuses people on this is that sometimes people will recognize, hey, Mr. Cottle, these aren't perfect squares. Are these impossible? Nope. Anytime you recognize your number out in front is not a 1, remember that your first step is to look for a greatest common factor, which in this case is going to be a 2. And when I take the 2 out, you'll see that now I have perfect squares. I'll put that 2 out front, and I'll get 4x and 4x, and I'll get a plus 5 and a minus 5. Similar on this one. Neither of these are perfect squares. That's a really good cue to look for a GCF. The GCF on this one is 3, leaving us with 9x squared minus 4. I'll place the 3 out front. I do need that 3. And then it's 3x and 3x when I square root the 9x squared. And when I square root the minus 4, it's 2 and 2. Those last two needed to have a GCF taken out before we could factor. So don't forget to look for one on every problem when there's a number with your x squared. Right, and you'll see if you watch any of the other videos that these are in standard form called ax squared plus bx plus c. Whenever a is not 1, you need to check for a GCF. So you could have factored this page without me giving you this lesson, but it is nice just to understand that these can be done very quickly, especially the two-term ones, because all you're doing is taking square roots.